Okay, so here's my third problem in solubility. It's another common ion problem, and it's one that I always had trouble dealing with for some reason or other. Probably because it's somewhat difficult, basically because of the assumptions that you need to make. Okay, so we have a 0.25 moles. We just have 0.25 moles. So I'm going to erase the A because that sounds stupid. Okay, so we have 0.25 moles of AgNO3 are dissolved in 1 liter of 0.6 molar sodium cyanide, and then we add 1 mole of sodium chloride, and we want to find out if the sodium chloride, or if the silver chloride, will precipitate. Okay, so let's ignore the sodium chloride part for now. Let's just focus on this first line. So we're going to have AgNO3, but we don't really care about NO3. We never really care about NO3 in solubility. It's always soluble. So we can pretty much just get rid of the NO3. And the same with sodium. That doesn't play a part in this reaction. So we can cross out our sodium, and we're left with what's important, our cyanide and our silver. So what's the reaction between cyanide and silver? Well, this should be given, so this is going to be in your book. So you have silver, and this attaches to 2 cyanides. Ooh, that's huge. And this is in equilibrium with Ag silver cyanide. And everything here is aqueous. So silver cyanide and silver cyanide are all aqueous. Okay, so now we have to make an assumption. We make an assumption that this is not an equilibrium. We'll go back to that later because it is equilibrium, but for now we're just going to pretend that this goes to completion and there's no more silver left in solution. So let's draw an ice table to see what the concentrations are after this goes to completion. Okay, so silver, we started with 0.25 moles and molar because it's 1 liter. So we have 0.25, and we are going to start with how many cyanides? We start with 0.6 cyanides, and we start with 0 silver cyanides. Okay, so now it's going to go to completion. So it's going to take up all of these silvers, because it's the limiting reactant, and you all know what that is. And that means that there's going to be subtract minus 0.5 from here, because it takes up twice as much, and it's going to add 0.25 over here. So that's going to give us equilibrium. It's not equilibrium. I should change this E to final concentrations or initial concentrations. I don't know. Initial concentration, other initial would be optimal, I guess. So it's going to be 0. It's going to be 0.1. And this is going to be 0.25. Okay, so now we're saying that, no, wait, this isn't in an equilibrium. Now we want to go backwards. Okay, so let's rewrite our equation and make a new ice table. So we have, and I'm going to write that a little bit higher. So this table isn't quite, even though it's pretty much touching the one above it, it doesn't go in sequence with it. It kind of does, but you'll see that. And now this actually is, we actually take into consideration the equilibrium. AgCN2. 2 minus. And we draw our ice table, as always. Okay, so now we plug in our values, because now we start with 0 silvers, we start with 0.1 cyanides, and we start with 0.25 moles of silver cyanide. And our change, well, we're going to add x over here, we're going to add 2x over here, and we're going to subtract x over here. So we're going to end up with x 0.1 plus 2x and 0.25 minus x. Okay, so these are our final concentrations, or I guess our equilibrium concentrations of our sodium and our cyanide and our sodium cyanide. Okay, something else that will be given in this equation is your Kf of the sodium cyanide. This Ksp relates to our AgCl. So our Kf for our silver cyanide is 5.6 times 10 to the negative 18 equals 5.6 times 10 to the power of negative 18. Okay. I'm going to draw a border here and pick a new color. So now we know the Kf, which is equal to 5. There's not enough room here. Okay, so I'm going to copy this ice table, I guess. Copy, delete. Oh no. Okay, I guess I will copy this part. Oh, it's laggy. And this part. And I will delete this. And I will paste it. Excellent. Okay, so that works good. Alright, so now for an equilibrium expression, we weigh our Kf, which is equal to 5. I'm sorry, something's on the bottom of my mouse, and I can't move it. So we have 5.6 times 10 to the negative 18 is equal to our AgCN, products over reactants. So we have AgCN 2 minus, and it's the concentration of that. It's not a very straight line. And then we have, that's over the silver ion and our cyanide ion. And we can all relate all these three concentrations by our ice table right here, because it all puts them in quantities of S, or X, rather. So we have AgCN2, and wait, also our cyanide is squared. That's important because there's two of them. So we have our AgCN2 is 0.25 minus X. And that is over top of our silver, which is X, times cyanide, which is 0.1 plus 2x. And this is squared. Okay, so now we can make the assumption, or it's important to make the assumption here, because we can't get rid of any square, and this Let me change colors, because we're going to be squaring this. That's going to produce an x squared, and we're going to be multiplying it by x. That's going to make an x cubed, so that's going to be hard as hell to solve. So we're not going to do that. We're going to assume x is small compared to 0.1 and 0.25. So what that allows us to do is get rid of this x. So and also get rid of this x. And we don't really care about this anymore, so we can cross this out. And now we have a quantitative equation where we have 0.25 over x times 0.1 squared, which is 0.01, and that's equal to 5.6 times 10 to the negative 18. So we're going to solve for x, and I'm not going to put all my steps in here because I'm running out of room, but assuming I did my math right, which might be too big of an assumption, we get 4.464 times 10 to the negative 19, which looks pretty good. And now we have this x equals the concentration of silver, which is important in calculating or determining whether or not this will precipitate. So now we have this equals the concentration of silver, which is important, and I'm going to put this onto a new slide. So copy, let's just get rid of no, I'm going to copy this too. Copy, get rid of you, paste, shit. Okay. There we go. Okay, so here we have 4.64 times 10 to the negative 19, and that equals the concentration of silver. So now how do we figure out whether or not it will precipitate? Well, we know that the KSP for it is 1.8 times 10 to the negative 10, which means our QSP has to exceed that. So our QSP is going to equal the concentration of silver times the concentration of dissolved chlorine. And we know the concentration of silver is 4.464 times 10 to the negative 19. And we're going to assume sodium chloride dissociates completely. We didn't even care about the sodium. So now what we care about is we added 1 mole of chlorine, which in 1 liter is 1 molar. So we're going to be timesing this by 1, which means it's going to, our QSP is going to equal 4.464 times 10 to the negative 19, which is, when you compare it to our KSP, which is 1.8 times 10 to the negative 10, we see that our QSP is much, much smaller than KSP, which means because QSP is smaller than KSP, there will be no precipitation. Okay, so I think that's all I'm going to be doing for the solubility. I'm pretty busy. I'm not sure I'm going to be getting any more videos up on solubility. I might do some on electrochemistry if it is wanted.